A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, Guwahati, instructor for the NPTEL MOOC course Pavement Construction and Technology, funded by Ministry of Education, Government of India. Our today's lecture will be a part of lecture under the module 10, where we will discuss about the structure evaluation of flexible pavements through two techniques, specifically using Benkelman beam, and the other one is by falling weight deflectometer. At the very beginning, I would like to acknowledge the use of text, information, graphs and images sourced from various textbooks, codal standards, journal articles, reports, newsletters and public domain searches. Now, structural evaluation, we may require to evaluate any constructed flexible pavement structure to get an idea about its current structure strength, and this may be required to ensure the quality of construction, or it may be many a times required whenever we require some strengthening of the flexible pavements. So, we want to work out what is the strength of the current structure and how much amount of overlay, or what is the requirement of the overlay for this particular pavement structure to serve a particular amount of traffic in coming years. So, structure evaluation of pavements manual and what it normally consists of. Here, under this particular evaluation, it involves applying a standard load to the pavement and measuring the response of the pavement in terms of stress or strain or in terms of the deflection. So, two codal provisions are there, specifically one is IRC 81, which is there for guidelines for strengthening of flexible road pavements using Benkelman beam deflection technique. Second is IRC 115, which is the guidelines for structure evaluation and strengthening of the flexible road pavements using falling weight deflectometer technique. So, here itself you can see these are the two different techniques which are used for working out the strength and to work out the overlay for strengthening of the flexible pavements. So, the structure evaluation of flexible pavements is widely done using Benkelman beam and falling weight deflectometer. These are the two techniques or the set of equipments which are used for structure evaluation of flexible pavements. Now, today in this particular lecture, we will discuss about the Benkelman beam deflection techniques for structure evaluation of flexible pavements. In 1953, Alvin C. Benkelman developed the Benkelman beam is to measure pavement surface deflection, specifically for the Western Association of State Highway Officials test road to obtain design flexible pavement overlay. Thereafter, continuous research have been done and a lot of exercises throughout the globe have been done on working out this Benkelman beam deflections to determine the overlay thickness for strengthening of flexible pavements. So, the Benkelman beam forms one of the earliest equipments used for measuring deflection, structure evaluation of pavements. In terms of the deflection measured, we can compare the different flexible pavement sections also, and is widely used across the world for evaluation of the requirements of strengthening of flexible pavements. So, that is one of the prime purpose of it, where we need to work out what is the requirement of or overlay for strengthening a given flexible pavement. And in this particular method of structure evaluation, a static load is applied to the pavement surface and rebound deflections are measured at one or more locations with the help of a Benkelman beam. You can see there is a vehicle where dual tire is there on one side. This is a beam whose probe is inserted between the dual tires, and then the deflection measurements are made. We will discuss them in detail. So, what is required in a Benkelman beam deflection study is the Benkelman beam first of all. So, it evaluates flexible pavements based on the principle that their performance is closely related to the elastic deformation that can occur under wheel loads. So, here we will use static loads and we will look into the rebound deflections which takes place. This elastic deflection or deformation depends upon several factors. If you have a pavement composition, a load is applied, some deflection will be there, deformation, or I will say deformation is there. This will depend upon several factors of the pavement. What are those ones? First of all, the type of subgrade soil, the subgrade over which the entire pavement crust is resting. So, it will depend upon the subgrade soil. its moisture content, what is the state of it, and compaction, how well it is compacted. Then other part is the thickness and quality of the pavement layers, what different layers, your granular courses, sub-base courses, base courses, binder courses, wearing courses. So, their thickness and their strength. So, thickness and quality of the individual pavement layers, the drainage conditions, how well the pavement is drained, and the pavement surface temperatures, because specifically the binder stiffness changes with the change in the temperature. So, if there is a good thickness of bituminous courses, then definitely that also plays a role. So, this deflection under a load which is used in this particular Benkelman beam deflection techniques in a manner will try to capture these informations of the pavement structure in a whole. So, Benkelman beam consists of a cylinder beam, a thin beam 3.66 meter long, pivoted at 2.44 meters from the tip. This is a side view you can see in this particular one. This is a beam which is of a length of 3.66 meter from here to here. This is the point where it is pivoted. So, 2.44 on this side, 1 point. This is not completely extended because of the limitation here on this slide. You can see here this is the one. So, it is pivoted at this particular one. So, and then you can see there are two legs are there, these are the front legs, and then there is a rear leg. So, you can see this is a rear leg, these two are the front legs of this particular one. So, and here is the one where this particular one is pivoted. Now, when it is inserted, this is the another one, when it is inserted between the dual wheels of a standard truck loading, this is a picture of the actual site. Now, what we do, again you can see a closer look where this probe of this Benkelman beam is inserted between a dual wheel, and then you are going to measure the deflections here. So, what is done in this one, pavement deflection is measured using the Benkelman beam by positioning this beam probe between the dual wheels of a loaded truck, standard loaded truck. I will mention those particular details also in the upcoming slides. Both rebound and residual deflections can be captured in this particular study, but what is we require for this particular exercise, specifically the overlay thickness determination, is the rebound deflection, which is directly related to the pavement performance and is critical parameter used as per IRC 81 for the design of overlay thickness for flexible pavements. The residual deflection again can result from the non-recoverable deformation of the pavement and also from the influence of the deflection balls on the front legs of the beam, because on the front legs of the beam how the deflection ball is affecting, this can also lead to some amount of residual deflections, but what we will require here for our overlay thickness design is the rebound deflection. Now, while conducting this particular exercise, Benkelman beam deflection study will initially, or we can divide it into two main components. One is the condition survey and second is the actual deflection measurements. So, this condition survey is done to collect some basic information about the road structure, so that we can divide into some homogeneous sections in that case. So, before measuring pavement surface deflections, this primary phase involves what is usually done. A visual inspection is done along with the measurement of rut depth, for which we can use a 3 meter straight gauge. So, and then we will divide the sections into three major categories as per the IRC 81 requirements, and what it says, a section can be called as good if the rutting is less than 10 mm and there is no cracking in that particular section. Fair if the rutting is between 10 to 20 mm, no cracking or cracking confined to a single crack in the wheel path. So, when this is there, that section can be called as a fair. This is a classification as per IRC 81. Poor rutting is greater than 20 mm, extensive cracking, sections with cracking exceeding 20% shall be treated as a failed sections in that case. So, I can broadly keep those sections which needs to be evaluated through Benkelman beam into these three broader categories: good, fair and poor. and because I'll always prefer to work out the overlay thickness, and I expect, or it is otherwise inconvenient if the overlay thickness is different in small sections of length. So I'll always prefer that the overlay thickness doesn't vary too frequently. So each section generally kept as a minimum 1 kilometer of homogeneous section. So for that, at least you will have one uniform overlay thickness, because otherwise it becomes impractical. However, in cases of some localized failures are there, or where more detailed inspections are required, the cases may be different, but otherwise we will prefer to have at least 1 kilometer section for one overlay thickness, which is worked out. Now, once this preliminary survey is there done, and the sections are divided into these three broad categories, then the deflection measurement study starts with it. So in each road section of uniform performance, at least 10 evenly spaced, so 1 kilometer I can have, and in at least 10 measurements have to be made in general, and the measurement should not exceed, and the distance between these measurements should not exceed 50 meter. This is another point. And if there are multi-lane roads, because the lanes may be distressed in different manner. Certain, if multi-lane roads may be there, the outer lane may be more distressed, the inner lane may be more distressed. So there may be a requirement to conduct this study on all the lanes. When we are doing it on the adjacent lanes also, we will prefer to do it in an staggered manner. So here you can see they are marking the points where by chalk, by a moving wheel, we can mark the point along the pavement edge where these measurements are to be taken up. Now, how far it should be there from pavement edge? Again, it is specified in IRC 81. It says that it can be 60 centimeter from the pavement edge if the lane width is less than 3.5 meter, and it can be around 90 centimeter from the pavement edge if it is more than 3.5 meter. So you can see the distance which is there from the pavement edge where these measurements are to be made. Now, for these measurement, as a standard load has to be used. So for this particular one, there should be a standard truck with a rear axle load of 8170 kg. So this is one important requirement. The truck should be fitted with dual tires, and the tire pressures should be of 5.6 kg per centimeter square. So this needs to be ensured while conducting this particular. So you need to have a truck which is loaded in such a manner that the rear axle weight, so that axle pads you require, or you can at a weighing machine or any weighing pads, you can ensure that the rear axle should have a 8170 kg of weight, and the tires are inflated to a pressure of 5.60 kg per centimeter square. This is the requirement for the standard static load which is to be considered. Now, when these measurements are made, as previously mentioned, there may be the correction which is required for specifically two factors. One is temperature correction, second is seasonal correction. Now, why temperature correction? As mentioned earlier also, the stiffness of binder changes with the change in the temperature. So the pavement structure may be soft at higher temperatures, may be stiff at lower temperatures. So it says the stiffness of bituminous layers vary with the temperature of the binder. Therefore, it is essential to correct all measured deflections to a standard reference temperature, and that temperature is normally taken as 35 degrees centigrade for the Benkelman beam deflection studies. Second is the seasonal variation. Now, with the season, because if I do some measurements during a rainy season, then the pavement may be in a weaker condition. So you may have higher amount of deflections which may be observed. So always one prefers to take these deflection measurements when the pavement is in the weakest condition, and that particular one will depend upon again certain parameter. So it is advisable to conduct deflection measurements during the period when the pavement is in its weakest condition. It's typically occur soon after the monsoon. Therefore, the deflection testing should be preferably carried out during this time to capture the most critical conditions. Now, but actually every time it is not possible to do the measurements at 35 degrees centigrade or to do measurements just after the monsoon is over. So then we need to apply the corrections considering the temperature and considering the variation in the season. So as I mentioned, The standard temperature which is preferred for Benkelman beam study in most of the tropical regions is 35 degrees centigrade for deflection measurements. In some certain colder regions at higher altitudes above 1000 meter, where the average daytime temperature remains 20 degree below 20 degree or for more than 4 months. In that particular case, it may be difficult to do this test at 35 degrees centigrade. So, there we prefer to go for 20 degrees centigrade. We normally go for measurements when the temperature is more than 20 degrees centigrade, and then you do not require to go for those temperature corrections also. So, these are for specific locations. Now, how the temperature corrections are applied? It says for temperature correction, it says that the deflection is expected to vary linearly with the change in the temperature. So, the measured deflection is adjusted corrected by plus minus 0.01 mm per degree centigrade deviation from the 37 degree centigrade. So, if the temperatures are less than 35 degree centigrade, then I need to add a value of 0.01 mm per degree centigrade. Say if the temperature is 32 degree centigrade instead of 35 degrees. So, 3 degree lower. So, the deflections will be less. So, here I will 3 into 0.01. So, 0.03 has to be added in the deflection. So, to get the corrected pavement deflections for the from the temperature point of view. So, add 0.01 mm per degree centigrade when the temperature is below 35 degree centigrade, and say if it is higher, say 2 degree higher, 37 degree centigrade, then I will deduct a value of 2 into 0.01 mm, that is 0.02 mm from the measurements which are obtained at 37 degree centigrade. So, temperature correction is, and this correction is specifically as mentioned because of the change in the binder stiffness. Now, there may be certain pavements which are very thin pavements, you do not have good amount of bituminous layers, thin surfacings are there, then you do not need to apply for these corrections, specifically like premix carpet is there, surface dressing is there. Or cases where these pavement structures are severely cracked, that is another cases where these surfaces are severely cracked, then also, or stripped bituminous layers are there, then also we do not need to apply these ones. And specifically it is mentioned correction is applicable only with the pavements having bituminous layers of more than 40 mm of thickness. So, when the thickness of bituminous construction is more than 40 mm, we are going to consider the temperature corrections. Now, the second correction, which is the seasonal correction which has to be done. Now, this seasonal correction, what factors it will depend? It will first of depend the subgrade soil, because that is the most which is going to get affected. Its field moisture content, as I mentioned, because every time it is not possible to conduct this particular exercise immediately after monsoon is over, when the pavement is in the weakest condition. So, we need to work out what are the what is the soil composition, what is the subgrade soil type, its moisture content, and what is the average annual rainfall in that particular area. So, these are the 3 parameters which are required, and for this one, for the seasonal correction, usually the soils are divided into 3 categories. The first is sandy and gravelly soil is there. Second is clay with low plasticity index, that is plasticity index less than 15, and third one clay with high plasticity, that is plasticity index more than 15. So, we divide the soil, the subgrade soil which is there in that particular section into these 3 broad categories, and then we will look for the rainfall in that particular region. So, for rainfall again 2 categories are there. One is when the annual rainfall is less than 1300 mm, second category when the annual rainfall is more than 1300 mm. So, for these 3 combinations of soil and 2 combinations of annual rainfall, moisture correction or seasonal correction factors have been given by IRC 81. And now you can see, to work out this because you need to have the soil sample to check whether what is the characteristic of it, whether it is a sandy soil, a gravelly soil, or it is a clay soil with what is the plasticity index. So, you need to obtain the soil sample. So, a test pit need to be dig near the pavement edge. You can see this is a test pit, and then the soil has to be taken out from a depth of say around 5 to 10 centimeter in the subgrade, and this normally depending upon where we go for measurement. So, it is usually in the range of 60 to 150 centimeter. So, we scoop out the soil from this particular. So, test pit is done, and then we try to scoop out the soil, and this is sealed, taken to the laboratory to do the gradation analysis and Atterberg limits measurements, and to get the idea about the whether it is in which out of these three categories it falls under which category. And then as I mentioned, IRC 81 have given the moisture correction factors for this particular one. So, different plots are there. Like the first one I will just read out: moisture correction factor for sandy gravelly soil for low rainfall regions. So, for this particular one, if the moisture content is there for that particular soil, you will work it out, and then you will see what is the moisture correction factor. So, this is here it is given for with low plasticity less than 15 and for high rainfall regions. So, this is how you work out the moisture correction factors for the soils which are scooped out, and usually you will prefer to go for this one at least in 1 kilometer one test pit, and this frequency can be further increased depending upon how much variation you are observing there. Now, once this part, the temperature is determined, and for temperature you can every hourly you can measure the temperature, and as I mentioned, for seasonal correction, this subgrade moisture correction, you need to work out the test pits preferably every 1 kilometer. Now, when the deflection measurements has to be start, as I mentioned, a standard truck has to be brought up with a rear axle weight of 8170 kg, dual tires assembled to this particular one. It is brought to that particular test location as mentioned, which is at a prescribed distance from the pavement edge, and then this Benkelman beam probe is inserted between these dual wheels. Thereafter, the first reading is noted down. Now, the first reading, and when, because initially you can calibrate this Benkelman beam, and then the dial gauge can be, say, for the initial reading it can be brought to 0 also, or you can directly note when no load is there, when load is brought, you note down the first initial reading. Now, this initial reading is to be noted down when in the dial gauge the deformation is less than 0.025 mm per minute, so that it gets stabilized, and then you note down the first reading. So, that is known as your initial reading. So, the dial gauge, these people are recording the first reading of this particular one. Now, and when this the variation deformation is less than 0.025 mm per minute, I recorded my first reading of the dial gauge. Then the truck are asked to move ahead for a distance of 2.7 meter. So, thereafter it is asked to move ahead 2.7 meter. So, all these points are from the pavement edge and along the length of the carriageway will be marked in advance, so that the truck will be directed to move to the next point. There again I will record the reading when this particular is less than 0.0, the deflection is less than 0.025 mm per minute. I will record my second reading, that is known as my intermediate reading. Thereafter, it is further asked to move ahead for a distance of 9 meter, and then the final reading is recorded. Again, when the recovery is less than 0.025 mm per minute. So, what I recorded in this particular one, the first reading where the probe was inserted, that was my initial reading. Second, when it was moved ahead by a distance of 2.7 meter, second reading. Then third reading when it moved ahead further 9 meter. So, I got my third, that is my final reading. Now, here in this particular one, because the beam is designed in such a manner, we need to work out the actual deflection which is there. So, for this particular one, what is done is, first of all, we will measure the difference between the final and the initial readings. So, the reading at once it has moved to 9 meter, that is 11.7 meter, that is the final reading. So, the difference between the final and initial, we call it final differential reading also. And another one is, we are going to work out the difference between the intermediate and initial. So, that can be called as intermediate differential reading also. And we are going to see whether how much difference is there between these two. If the difference is within this particular range, then the actual pavement deflection is considered as twice the final differential reading, because what it records is half of the deflection. What we are getting on the dial gauge, it is half of the deflection. So, we are going to do, because this is how the Benkelman beam is also calibrated using some blocks of standard thickness, we can calibrate it. So, whatever we got, if the difference between the final differential and intermediate differential is less than 0.025, then in that particular case the final differential reading will be called as your actual deflection. So, that is, if this difference is more than that, then we have an apparent pavement deflection, which is again the twice of your final differential reading, but then you need to get the true deflection also. In the first case, when the deflection, this difference was less than this one, the final differential reading twice of it became your true deflection, or I can say the actual pavement deflection. But in the second case, when this may be more than that, then this final differential reading will become your, instead of actual, it will become as your apparent deflection reading. And for getting the true deflection or the actual deflection, you have to add to this apparent deflection a value which is 2.91 times the difference between the final and twice the difference between the final and the intermediate readings. So, in that case, true deflection readings have to be worked out. So, one is, this is your final differential minus intermediate difflection. If this is less than 0.025, then twice of your final differential reading will be your actual deflection. If this is not there, then what is this twice of your final differential reading is your apparent deflection. To that particular one, you need to have to work out, this is 2.91 times twice of your final minus intermediate readings. So, this and that gives you the true deflection. So, from this particular one, what you get is your actual pavement deflections. This is the exercise which is there. Now, once you get this actual deflections, first you will apply the temperature corrections to it. So, whether at what temperature you conducted this particular study, so accordingly you will apply temperature. And how can I measure the temperature of a pavement course? Normally, I will dig a hole in this particular one for a depth of around 40 to 45 mm, and the dia of the hole may be around 1 centimeter. I will pour glycerol roll it, and I will insert a thermometer. I will wait for a time of around 5 minutes. I will get the reading. So, I will get my pavement temperature. So, this is how I can work out the pavement temperature. Once that this, so this true deflection is there, actual deflection, you will apply the pavement correction, and then on this temperature corrected reading, we will apply the moisture correction factor. So, we will multiply those temperature corrected readings with the moisture correction factors, and that gives you your final corrected reading. So, this is the two steps are there. First, temperature corrections are applied, and second, the moisture corrections are required. So, you get a corrected reading. Now, here in this particular one, we do not work out the overlay thickness just on the basis of one measurement. I mentioned that 10 measurements at least has to be done in one section, and the distance should not be more than 50 meter. So, on the basis of those number of measurements, we will work out the mean and the standard deviation. So, here you can see on the basis of those true corrected deflections, we will work out the mean and the standard deviation, and it is suggested that from this one you get the characteristic deflection, which is used to determine the overlay thickness. And that characteristic, what is that characteristic deflection? It is your mean plus twice of your standard deviation if you are looking for higher categories of roads, which are national highways and state highways, and this characteristic deflection is mean plus standard deviation for other categories, like it may be say for rural roads or major district roads in that case. Now, once you have this characteristic deflection, there you can see this is the plot which is there with the between the characteristic deflection and the overlay thickness corresponding to different design traffics. Now, design traffic, normally whatever overlay you will be requiring for it, you will target it for a period of say at least 5 to 10 years. So, you need to work out the design traffic which is going to come up in those 5 to 10 years. Specifically, usually it is designed for a period of 10 years. So, the design traffic for this particular one, already IRC 37 states how you work out the design traffic. This is the NS is the design traffic in terms of standard access to be encountered. Here you can see it is 365 into A 1 plus R raised to power x minus 1 by R into F, where you have the lane distribution. It says the R is your annual growth rate of commercial vehicles, design life, and you have along with this there is a lane distribution factor also which is to be there. ADF, lane distribution factor. So, cumulative standard vector to be catered in the design, initial traffic in the year of completion of construction in terms of commercial vehicles, per day dueling assigned to account. Okay, now in this particular one already it has taken care of the lane distribution. So, you do not have to apply for the lane distribution factor separately. And then the design life, as I mentioned, this is as per IRC 37 you need to work out the design traffic. So, once you have the design traffic, so it may be say the design traffic may be for this coming 10 years is 100 MSA. So, you have the design traffic which is 100 MSA here, and you have the say for an example you have a characteristic deflection obtained from the previous your mean and standard deviation as 4. So, then you will see and work it out how much amount of overlay thickness you get. So, I will see from here possibly this particular one may be say around somewhere around 295. So, 295 mm of overlay thickness is required for this pavement structure. Now, this 295 which is given by for this particular example which is given by IRC 81 is in terms of bituminous macadam only. So, but you will not go for a wearing course in terms of bituminous macadam. You will prefer to go either in case of some binder layer or a wearing course layer. So, it may be in terms of DBM or BC. So, this thickness in case if you are providing in terms of DBM and BC, it will become 0.7 times of what 295 is there. And if this is more enough, you need to provide some, the structure is weak enough, you may require to put up some granular layers also. Then the granular layer will be thickness will be 1.5 mm of this overlay thickness in terms of obtained in terms of bituminous macadam. So, this is how this Benkelman beam deflection study is done, and the measurements helps you to work out the overlay thickness by this simple technique. So, this is one way of doing the structure evaluation and working out the overlay thickness for flexible pavements by the Benkelman beam study. Thank you.